this video, we're going to talk about expected value. Before we talk about that, let me talk about the law of large numbers. And that is, if you conduct an experiment over and over again with independent trials, then what they call the relative frequency, which is the data percent, gets closer to the theoretical probability. Let me show you an example of that. So Theo rolled a standard six-sided die 1,000 times and ended up getting 100 or two popped up 100 times. And he's worried that the die isn't fair. And his theory, the problem of getting two, or I should say the probability of getting two, is 1 out of 6, assuming that they're all equally likely. And if you divide that, that's 0.17. But that's 100 out of 1,000, or 0.1. A 10% chance versus a 17% chance, which is significantly different. I mean, it's almost double the odds, theoretically speaking. So this is quite different, especially for 1,000 times. You would expect it to be much closer to 17%. So I think he's right. I think there's a problem. So my answer is he correct? Yes. Those two are far too different to assume that somehow maybe this die isn't weighted. Now, the law of large numbers actually lends us to something called gambler's fallacy. And it's the idea that you believe that after a while, your bad luck is going to stop, meaning you're due to have some good luck. Okay. That's just not true because the odds are not in your favor when you're gambling. They're not. And therefore, the odds of you losing over and over again aren't that low. The odds of you winning over and over again would be very low. So gambler's fallacy is kind of builds on the idea of law of large numbers. People believe that after a while you're expecting to see it, but it's not really all that unlikely for you to just keep losing. Value is the long run average or mean when you repeat an experiment. So any casino has the expected value of a game set up in their favor. In other words, they expect, even if you win sometimes, for them to always come out ahead. And how you calculate the expected value is it is the sum of each outcome that we're interested in times the probability of that outcome. I'm going to write it like that. Or X times the probability of X, where I'll label X to be these outcomes. So let's look at an example. A lottery ticket has 5 possible prize amounts and the chances of winning. So this would be my X, the prize amounts, and P of X, the probability for each. And you'll notice the highest category happens to be the last one, where there's a 0 chance of it happening. Okay. So let's calculate the expected value. That means I'm going to take each prize amount and I'm going to multiply it by its probability. So 1 times 1/5, 10 times 1/50, 50 times 100, 1,000 times 1/2,000. And honestly, this last category, but it makes sense to include it because that is one of the outcomes. One of the outcomes is you're not going to win anything. So plug that into your calculator, get a decimal. You don't have to do fractions, get a decimal. And I got 140. So what that means is I expect to win out that the ticket costs something. And if the ticket costs $2, that means with my winnings, I'm really expected to lose 60 cents every time I buy a ticket. So even if sometimes I win and maybe even win pretty big, like the $1,000 one, it's not going to overall make up for all the times I've lost. Let's look at another example that uses expected value for their favor. Insurance companies. Oh yeah. The insurance company has these policies here. Sorry, I just realized that the cursor's hovering over the screen. Let me put it up here. It's going to pull up the keyboard. I'm sorry. Let me scroll back down. There we go. All right. So an insurance company somebody sells a policy, and in the end, even though they'll pay out, set up our table for this example. So let me give myself some space here. And I don't really need that big of a table. So X and P of X. Okay, so 1 in 50 policyholders will file a $6,000 claim. Okay, so $6,000 comes out 1/50th of the time. 15,000 comes up 1 in 100. I have 33,000 comes up 1 in 300. And then I do have a last category that I could bother calculating, which is 0. And honestly, I don't need to, but I'm going to, because I want you to see where this information could come from. So the idea is these all are going to total up to 1, because it's going to represent all possibilities, all 100% possibilities. So I need to figure out how much the first 3 total up to. So I'm going to do that over here. 100th, and 1/300th. Now, if you have a calculator and you know how to do fractions, go for it. Do the fractions. I'm going to do it by hand. So I'm going to get a common denominator of 300. So that gives me 6/300 plus 3/300 plus 1/300, which is 10/300, or 1/30th. So those add up to 1/30th, which means in this last category, then it needs to be 29/30ths to add up to 100. So if those 3 total up to 1/30th, I need another 29/30ths to get 1. All right. I'm going to erase my work here. We don't really need that for the back. So 6,000 times 1/50th, 15,000 times 100th, 33,000 times 1/300th, and I really don't need the last category, but I'll include it anyways. 0 times 29/30. And if you plug that into your calculator, I got 380. So on average, they're going to pay $380 per policy, but they charge $1,350. So for them, they're going to, even if they're paying out, they're going to end up bringing in, let's see, 1,350 minus 380 comes out to 970. They're going to make $970 on each policy of money, even when they make these big payouts periodically.